Welcome back, focused learners. Today, we are stepping into the shoes of the ultimate time traveler. What if I told you that you could see your completed, perfectly graded exam paper before you even walk into the hall? Well, that's exactly what we're doing today. We are working completely backwards from success. If you're tackling the Cambridge AS and A-Level Computer Science 9618 syllabus, or honestly even building foundational knowledge for a 0417, 0478, 0983, 0984, or 22110, this explainer is an absolute game changer. We're zeroing in on a notoriously tricky topic, the effects of changing image resolution and color depth. Mastering this specific area doesn't just earn you marks, it trains you to see exactly what examiners are hunting for across your entire paper. We're going to completely deconstruct the core concepts, the methodology, and the critical analysis you absolutely need to succeed. So grab your notebooks, get comfortable, and let's decode the examiner's playbook. Okay, let's dive straight into this. Here's our clear, systematic roadmap for today. We're starting with the 15% secret, moving into the core principles and theory, then breaking down our procedural framework, tackling critical analysis, and wrapping up with the absolute top examiner warnings. Section 1. The 15% secret. The hidden weight of resolution and color depth. Now, you might be wondering, why on earth are we dedicating an entire deep dive explainer to this one specific concept? Well, here is the harsh reality of the exam room. Let me introduce you to two typical students. We've got Alex, who overloads their answers with raw computer science facts, memorizes every textbook definition of a pixel, but provides absolutely zero analysis. And then we have Sam. Sam always rushes, panics against the clock, and completely misses the command word requirements. Both Alex and Sam usually lose massive points on this topic. Why? Because questions related to the effects of changing image resolution and color depth account for approximately 15% of the total marks in Paper 2. That is a massive foundational pillar of your final grade, 15%. It relies entirely on your understanding of how these visual metrics interact. If you're like Alex or Sam, you're leaving a whole grade boundary sitting on the table. But before we continue and fix Alex and Sam's mistakes, subscribe to our YouTube channel AC Exams at acexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Section 2, Core Principles and Theory. What the assessment framework actually wants from you. Let's break down the computer science specific assessment objectives. Examiners are targeting distinct cognitive domains here. First, knowledge and understanding. Do you know what a bit depth is? Second, application. Can you calculate the file size? And third, analysis. Can you evaluate the impact? But listen closely, because here is the real secret weapon: cross-topic connections. Top-tier candidates, the ones scoring the A stars, don't just memorize isolated facts. They understand cause and effect. They know that increasing color depth from, say, 8-bit to 24-bit true color doesn't just improve the visual quality of the image, it directly, mathematically increases the file size. And what happens when a file size balloons? It severely impacts transmission speed over a network, consumes more bandwidth, and eats up storage space. That's the cross-topic integration examiners are literally begging you to show them. You have to decode the command words. If the question says evaluate, they don't want a definition. They want the whole interconnected story. This brings us to a crucial realization. There is a massive, gaping chasm between an average answer and an outstanding one. Superficial breadth, which is what our student Alex does, just listing disconnected facts like a broken encyclopedia, simply won't cut it. The academic benchmarks prioritize logical, structured reasoning and deep analytical depth. So, how do we fix Alex's answer? We introduce the Peel framework: point, evidence, explanation, link. You make your point about resolution. You provide evidence, like the specific pixel dimensions. You explain how that affects the bit depth calculation. And finally, you link it back to the overarching system performance or user experience. When you write using Peel, you naturally force yourself into analytical depth. You stop writing down a wide breadth of shallow facts, and you start writing like a top-tier candidate. Section 3, the procedural framework. The method mark strategy. Knowing the Peel theory is great, but how do you actually process these heavy exam questions under intense time pressure to guarantee points? We need a system. We have a clear, 5-step procedural algorithm right here for tackling examination questions on resolution and color depth. Step 1, deconstruct the question. Identify that command word instantly. Is it describe, calculate, evaluate? Step 2, extract the relevant data. Pull out the image dimensions and the bit depth from the scenario. Step 3, select the analytical framework. This is where you decide if you need a mathematical formula or an evaluative peel paragraph. Step 4, execute with clear notation. Write out your working logically. Step 5, present your results with the absolutely correct, precise terminology. Following this sequence ensures you aren't just guessing in the dark. You are systematically and confidently breaking down complex problems, just like a compiler breaks down code. And keep in mind, this procedural mindset isn't just for written theory answers on paper too. Algorithmic thinking in computer science requires the exact same discipline. Think about it. It's step-by-step decomposition of a problem, data structure selection, efficient code implementation, and rigorous testing. Whether you are calculating the memory required for a high-resolution bitmap image or you are designing a loop structure in pseudocode, the structured, logical approach remains exactly the same. You have to be meticulous. Now, I need you to pause and listen to this direct alert straight from the principal examiners. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. Think back to our student, Sam. Sam rushes, Sam tries to calculate the image file size in his head, writes down the final number, gets a single 0 wrong, and scores 0 marks for a 5-mark question. Don't be Sam. Showing your clear step-by-step working is an absolute survival tactic. If you make a silly arithmetic error calculating file size based on resolution, but the examiner can see you multiplied pixels by bit depth and divided by 8 to get bytes, your method marks will catch you before you fall. You will literally salvage 3 or 4 marks out of 5, even with the wrong final answer. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Section 4, Critical and Comparative Analysis. Thinking like a top-scoring candidate. Welcome to the interactive workshop part of our session. Top-scoring candidates demonstrate their expertise by using 4 specific evaluative thinking traits. I want you to imagine a complex scenario. A client needs to store thousands of medical x-rays. They need high detail, but storage is limited. How do you evaluate this? First, multiple solutions. You consider various approaches, maybe compression versus lowering bit depth. Second, trade-offs. You actively analyze the pros and cons. You write about the balance between crisp, high-resolution diagnostic quality and restrictive server storage requirements. Third, limitations. You acknowledge system constraints, like bandwidth caps when transferring these images between hospitals. And fourth, evidence. You justify your decisions logically using exact formulas. You don't just say it takes up a lot of space. You calculate exactly how much space and use that as evidence. This is the difference between an average grade and top-tier excellence. Let's tackle a speed challenge right now. I want you to mentally find the flaw in this common student approach. A question asks to compare a low-resolution image with a high-resolution one. Sam writes, the high-resolution image has more pixels and looks better, but the low-resolution one looks blurry. Sounds okay, right? Wrong. That is losing marks. Here's a major pitfall in comparative analysis. It's simply not enough to just point out basic visual differences. You have to explicitly identify both similarities and structural differences. You need to use comparative connectives, words like whereas, conversely, or in contrast, supported by technical evidence to draw conclusions. A better answer using PEL would say, both images use a raster grid format. However, the high-resolution image utilizes a significantly larger matrix of pixels. While this increases the visual fidelity for the user, it conversely requires an exponentially larger amount of secondary storage. Boom! That is exactly what the examiner wants to read. Section 5, Top 3 Examiner Warnings. Avoid these common pitfalls. We are going behind the curtain now to look at the final system. If you want to guarantee top marks, you decode command words, you use PEL, and you manage your time. But looking directly at the historical principal examiner reports, we see 3 brutal traps where students consistently lose the most marks. Number 1, confusing cause and effect. Students often state that a larger file size causes higher resolution. No, it's the other way around. The higher resolution causes the larger file size. Number 2, forgetting boundary conditions and edge cases when evaluating a system. If an image is 1-bit monochrome, that's an edge case. How does compression handle that versus a 24-bit image? And number 3, providing generic, memorized answers that completely lack the specific context requested by the scenario. If the question is about a web designer uploading photos to a slow-loading website, your answer must explicitly talk about user loading times, not just abstract memory bytes. Apply your knowledge to their specific scenario. Here is a highly effective, practical strategy to help you retain all of this dense terminology. I actively encourage you to pause this explainer right now, take out a real piece of paper, and create a personal mnemonic using the first letters of the key terms we discussed today: resolution, color depth, file size, bandwidth, transmission. Lock in that terminology so it is instantly, automatically available to you when the clock is ticking down in the exam hall. Students who implement these computer science strategies see an average improvement of 2 whole grade boundaries. But let's be real, that only happens if they practice consistently with our weekly videos. So here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Seriously, don't let another exam pass you by without having this strategic advantage. We have covered a tremendous amount of crucial ground today, from the 15% secret to mastering the Peel evaluative thinking traits. So I will leave you with this final, provocative thought. If you were the examiner looking at your own past paper right now, would you award marks for your analytical depth, or would you be forced to deduct them for confusing cause and effect? Be honest with yourself. Think about that as you prepare. Challenge yourself to rigorously apply this deconstruct, solve, evaluate method in your very next practice session. Drop a comment below with your target grade for computer science and the biggest challenge you're currently facing. Our team literally responds to every single comment. Like and share this video with a study partner who needs it. AC Exams, your Cambridge success starts here. Keep learning, keep structuring those answers, and I'll see you on the next explainer.